We've talked a lot about forces and fields, and now I think we need to work a problem and see if we really understand how to apply them. Here's a simple problem. Find the net force on Q2 given the following information. So Q1, Q2, and Q3 are at 3 corners of a square. Q1 and Q3 are equal in charge, and they're equal to 5 microcoulombs. The coulomb is actually a very large amount of charge. So typical charges are much smaller than a coulomb. Usually they're microcoulombs. It's a very common unit to see for charge. Of course, a microcoulomb is 10 to the minus 6 coulombs. Sometimes you see millicoulombs, 10 to the minus 3 coulombs, but microcoulombs are very common, 10 to the minus 6 coulombs. Q2 is 2 microcoulombs. All of our charges are positive, and the spacing, the side of the square, is 0.1 meters. Now what you should do is pause the video and try the problem yourself. Come back after you've attempted it and then watch me solve it. Welcome back. What I'm going to do is first look at forces, and we'll just deal with forces, and then let's look at fields and see how we could have solved the problem using fields. With forces, we know that if more than one force acts on an object, we can just add them up. It's called the principle of superposition. You add up all the forces acting on the object. Of course, it's vector addition, and you get the net force acting on the object. So let's take a look at the force on Q2 due to Q1. Force 1 on 2. The force on Q2 due to Q1 is K times the charge of Q1 times the charge of Q2 divided by the distance between them squared. We'll plug in some numbers. Now, if I'm just looking for the magnitude of this force, I would just use the magnitude of Q1 and the magnitude of Q2. Those could be positive or negative. In this case, all of our charges are positive. Let's plug in our numbers. K, 8.99 times 10 to the 9th. Q2, 2 times 10 to the minus 6 coulombs. Q1, 5 times 10 to the minus 6 coulombs. And the distance between them, 0.1 meters squared. So when we plug in all these numbers, we get 8.99 newtons. Now, of course, we need the direction. So Q1 and Q2 are on the y-axis, and they repel each other. They're both positive. So if I use red for my force from 1 on 2, it would be pushing, the force would be pushing Q2 in that direction, in the positive y direction. So I need to put here j hat or y hat or an arrow in that direction. But we need to signify that this force is in the positive y direction, towards the top of the page. Now we do the same thing for the force from 3 acting on 2. And the force is K, Q2, Q3 over the distance between Q2 and Q3 squared. And when we plug in the numbers, we get 8.99 newtons. Now let's find the direction. This is the magnitude. Let's find the direction. Q2 and Q3 are lined up horizontally with one another. The force will be either toward or away from Q3. And because they're both the same charges, they repel each other. Let's use green for this charge. And the charge will be pointing in that direction. So that would be 8.99 newtons, and it would be in the negative x hat direction, or negative I hat. It's to the left. So to get the net force, we would add these together. We would have a force of F3 acting on 2 plus the force of F1 acting on 2, and that would give us this net force acting on charge 2. So we would have a magnitude of the square root of 2 times 8.99 newtons, and the direction would be at that 45-degree angle. That's using forces. We could have also found the net electric field at the location of Q2. And once we had that, we could have multiplied that by the charge Q2, and we would have had the force on Q2. So we could have said the electric field is equal to the electric field due to Q1 plus the electric field due to Q2. The electric field due to Q1 is K Q1 over R squared. And we want to know the electric field at this location where Q2 is, due to Q1. So the R is the distance between Q1 and Q2. In this case, it's just A. When you use equations, get in the habit of thinking about what each variable stands for. What is it? The distance between what? The distance between our point of interest, where we want to know what the electric field is, and our point charge that's creating the electric field. That's what we're looking for here. And of course the direction would be y hat or j hat. The other one, this should be a Q3. Q3 is also contributing to the net electric field at the location of Q2. And it's going to be K times Q3 over its distance squared. And it's going to be pointing away from Q3. It's going to be pointing in the negative x direction. Using our unit vector notation, it will be minus x hat or minus I hat. Those are unit vectors. And we add these up, and we get the same. And then we multiply it by Q2 to get the force on Q2. So we could have done that path also. Either way, we get the same answer. Hopefully you got that okay. How about we check to make sure? Let's add a part B to this problem. What charge should be placed at the empty corner of the square such that the net force on Q2 is 0? So what I'm asking is, what charge should be placed right here at the empty corner of the square such that the net force on Q2 is 0. So pause the video and see if you can figure that out, and then come back and check. This is a summary of the situation. The net force due to Q1 and Q3 points up and to the left the way I drew it here. And we're going to put another charge, I'm calling it Q4, at the empty corner of the square. And we want to make the net force on Q2 0. So what sign does Q4 have to be? Does it have to be positive or negative? In order to negate this force, in order to cancel out that force, we have to have a force in this direction due to Q4. It has to attract Q2. So it has to have the opposite sign of Q2. It has to be negative. Q4 has to be negative. Now let's find the magnitude of that force. We know the magnitude has to equal 12.7 newtons. It has to be equal in magnitude. This force and this force have to be equal in magnitude. And we know it's going to equal K, Q2, Q4, that's over R24 squared, the distance between them squared. And I'm just finding the magnitude here, right? Because I already know the direction it has to be, and that gave me the sign of Q4 was negative. So this just gives me the magnitude of Q4. So I plug in my numbers. The diagonal of that square is the square root of 2 times the length of the side. So I can solve for Q4. I get 1.41 times 10 to the minus 5 coulombs for the magnitude of Q4. That's 14.1 microcoulombs, 14.1 times 10 to the minus 6. And of course we know Q4 is negative, so Q4 will end up being negative 14.1 microcoulombs.